Hi everyone. Today we'll be looking at the mechanics of a very unusual new type of surgical robot. Surgical robotics has been developing for a while and has revolutionized surgery by reducing the invasiveness of surgical procedures to improve patient outcomes and reduce recovery times. Consequently, the market for surgical robotics has been steadily increasing, with the last 4 years averaging around 9% growth per year. The predictions for future growth vary, but all market analyses expect that it's a very promising field. There's a lot of very complex mechanics design that goes into surgical robotics, and it's a great topic for mechanics analysis. Just a few years ago, a research group at MIT described a new type of surgical robot that's just a small beam made of rubber filled with magnetic particles. The beam is small enough that it can move through arteries. The magnetic properties of the beam allow its shape to be controlled using external magnetic fields, allowing the beam to be guided through the body remotely. As you see the beam snaking through the artery, they're changing the direction of the magnetic field to get the beam to bend in different directions. The applied magnetic field creates torques on the magnetic particles that cause them to want to rotate, effectively creating a small moment at each of the particles. We'll be analyzing the deflections of these types of magnetic beam robots. If you're using the Mechanics of Materials textbook by Craig and Taylif, the content on beam deflection is in sections 7.3 and 7.4. When a beam is deforming, we often want to know what's the displacement for it from its original position at a certain location along the beam. The location along the beam is given by x in our case, and the beam deflection is denoted by small v, which is what we usually use for displacement in the y direction. We indicate the beam slope using theta. The method for determining the beam deflection is based on a series of differential equations that relate our distributed load. We're going to formulate a question in which we analyze the displacement of a magnetic beam robot to accomplish a goal. The robot is inside of an artery, and we want to apply a magnetic field so the beam displaces downward by 2 millimeters and applies a force of 10 millinewtons on the plaque inside the artery. Magnetic actuation is quite unique in that it creates a distributed moment, which is probably something that you haven't seen before. I'm actually not even aware of any other situation other than magnetic systems where distributed moments exist. But it's a great way to test our knowledge of mechanics in an unknown situation. The process we'll use is to first determine our equilibrium equations, then determine our equation for the moment in the beam, followed by integrating twice to find the beam slope and the beam displacement. Finally, we'll substitute in our boundary conditions to solve for the constants of integration and the value of the distributed moment. Like usual, we'll start by drawing our free body diagram. We're approximating our beam robot to be fixed at a reference point, which is definitely not true, but it's necessary to make the calculations reasonable. At the fixed end, we then have a reaction force, By, and a reaction moment, Mb. At the far end, at point C, we have a point force of 10 millinewtons pushing upward. Similar to how we usually approximate a distributed load as a point force when making free body diagrams, here we're writing our distributed moment as a point moment in the middle of the beam with a total magnitude of distributed moment times the length. We can write out our sum of forces in the y direction and our sum of moments. In this case, I want to consider a kind of side question, which is this structure determinate or indeterminate? If we were to draw something that looks like this, we can see that it's definitely indeterminate because we have 3 reactions and 2 equations. We could draw a free body diagram that looks like this. I usually draw free body diagrams with reactions in blue and external loads in red. However, in our particular case, it might be more instructive to draw the unknown values in blue and the known values in red. We can see that we still have three unknowns. It's just that in this particular question, our reaction at C is a known value because we've already been told that it's 10 millinewtons. But our applied load, our distributed moment of m naught, is unknown. And this is what we're intending to solve for. So we can consider this as a kind of indeterminate question. Okay, so getting back to solving the question, now that we've determined our equilibrium equations, our next step is to determine our equation for the moment in the beam. We'll take a cut at an arbitrary location, draw a free body diagram, and do a sum of moments at the arbitrary location x, which gives us an equation for the moment at any value of x along the beam. Even though we probably haven't seen a distributed moment before, we can see that we can take it into account the same way as any other moment. The only difference is that now the magnitude of the moment term varies with our value of x. Before we start integrating, I like to write down our boundary conditions. At our fixed point, we have boundary conditions that our slope and deflection are both 0. However, we have another boundary condition. We know something about what's going on at the other end of the beam. The vertical displacement is 2 millimeters in the downward direction. This type of boundary condition is certainly a lot less common, but we do see it sometimes. Now that we've determined the moment equation and the boundary conditions, we can start the exciting part, doing all the integrals. Our beam slope is 1 over EI times the integral of the moment, giving us one constant of integration. Integrating again gives us the beam deflection and another constant of integration. If we sub in our first two boundary conditions, we find that both of our constants of integration are 0. We can finally sub in what we know about our reactions MB and BY, and we got this information from our equilibrium equations, and that allows us. We'll just copy that equation again on the next slide. We have one boundary condition that we haven't used yet, and we can sub that in to get an equation that finally has only one unknown. We can multiply both sides of the equation by 3ei over L to the exponent 3 and rearrange to solve for m naught. When it comes to subbing in the numbers, I like to always use SI units, so I'm using 80 million pascals instead of 80 megapascals for the Young's modulus, and I'm using 0.05 meters for the length. We're also subbing in our equation for the second area moment of a beam with a circular cross-section. Finally, solving us gives us a distributed moment of negative 13 millinewtons. So we've solved the problem at this point, but let's take a closer look at our last equation. The last term represents the distributed moment that needs to be applied to create the force on the plaque. It makes sense that this distributed moment is proportional to the force because they both have the same units of newtons. I also want to make a brief comment on alternative formulations. We've analyzed this robot by treating the magnetic force as a distributed moment. However, we could also treat this as a distributed load. When the beam slope is small, the distributed load is an extremely good approximation of the deformation created by the distributed moment. So it's still very accurate from a technical perspective. If you're an instructor considering this topic as a quiz or assignment question, the distributed moment approach is a way of testing conceptual understanding by introducing a new concept, while the distributed load approach is a way to test concepts from class in the context of an emerging application. So in summary, we talked about surgical robotics as a fast-growing industry that requires complex mechanics design. We saw how magnetic beams can be approximated as distributed moments. We saw an example of non-zero boundary conditions. In this case, we had a target displacement of negative 2 millimeters at the end of the beam. And we applied the second-order integration method to solve for the beam displacement.